it's time for us to get started. I'm glad to see everybody who was able to make it to this session. The first thing that I want to tell you is our last test ended with integration, but not an integration of vector value functions. So what's new from the test one? First, in small part, was we concluded chapter 6, which mainly ended with integration of vector value function. There was some ending to the chapter having to do with these curves, and those are things that I want you to be familiar with, but in truth, I probably will not ask a question about it, about these types of curves. That's more associated to complex analysis, and so if you take that class, you'll be studying those more in depth. Okay? But about vector value functions, the integration of them, we are going to have something about that. And then we've been talking about series, mainly of complex sequences. Complex is the right thing to say because even if they're real sequences, they're complex sequences. And we're almost done for this, and it's in chapter 3. So in analysis 1, we covered chapter 3 mostly, but not completely. And we picked up what we skipped during this class. That's what's happening. All right. Well, with that being said, I want to tell everybody, and people are very on top of receiving information, and I just emailed about 45 minutes ago homework. And so I have copies of it right here, and I want to hand out hard copies to you. My handwriting, as we all know, is not beautiful. And so if you want to ask something about it, you can in terms of visualness. And I want to spend just a little time talking about some of the problems. Thank you. Okay, as you take a second to look over this homework, let me tell you where we're going. We're also, so we have half a lecture left to conclude the chapter 3, the series material. Half a lecture left. So the second half of that lecture will be in chapter 7. Which will deal with sequences of functions and their convergence. And so that's what we're going to be the main topic from that chapter. But we're not there yet. I say that only to tell you that we have made some adjustments to the syllabus in not what the coverage is really. This is what I planned on doing, is what I'm telling you here. But rather the dates that we'll be meeting. So today is the 8th. We're meeting today. We're here. And then we're meeting the 22nd as opposed to, I initially listed the 29th, then I said the 6th. And so the 6th we can meet. You can take your exam if you like on the 6th. And I think one person has contacted me and said they would like to take their exam on the 6th. But let me say this. I'm going to be here on the 6th. And so you can take your exam if you want to. And if you want to wait till the 13th, you can. And if you decide to come on the 6th to study, I will help you study on the 6th as well. So I just give that option to you, okay? So you know, you're welcome to come anytime. If you let me know, pretty much unless something's going on that would prevent me from coming, I'm going to be here too, okay? So the upshot is we're meeting on the 22nd. In that period of time between now and the 22nd, I'm going to do my best to put up 8 more videos. So that's 4 a week, and that will end the term, end the material. So I'm thinking by the 22nd, we're done with the material. That's what I'm going to do my best to do. And then the test will be on the 6th to the 13th. Okay? That's what I'll try to do. And it'll be around 33 or 34 videos. Okay? That's where we'll be at, somewhere in that range. And you might have noticed that the videos are getting a little bit longer at times because it's hard to stop in the middle of something. So they're long. That's what I think it'll take, 8 more videos, something like that. Okay, so that's the information that I have for you in terms of the setup for the class. You're more than welcome to have input on that type of setup for the class. So if you say, look, I asked some people before we got started, you know, I'd rather we hadn't met today or as often as we're meeting. Long drive. You know, if it's not necessary. I'm not thinking something good or bad about those type of comments, except that they're beneficial for us to do something different if it's better. So you don't have to be quiet about speaking your mind. I'm not going to take it personally. And if you say something, oh, this was wonderful that you, I'm not going to take it as an inflated ego either. It's not going to make me feel good either. Because I also drive an hour and 20 minutes to get here, which I'm happy to do. But I'm happy to stay home sometimes too, just like everybody else. That's the way I feel too, but I'm happy. Okay. Having said that, I would like to spend some time today talking about the homework. We just got it.
What does it do?
It's going to be due on Wednesday. I think that is not this coming Wednesday, but let's see, that would be, I think it's the 19th. And I sent an email, Dennis, that said when it's due, but I think it's the 19th, Wednesday the 19th. And so we're going to meet on the 22nd, and I'm hopeful to have them graded and handed to you on that day. So we'll be doing that.
Dr. Wicker, will we have a 4th assignment as well, or will this be the last one?
I think we're going to have a 4th assignment. And so it'll cover Chapter 7. That's what I think. Yes, ma'am, I sure do. That is what I'm thinking. But Ashley, one of the things that I think needs to be taken into consideration is doability. I mean, anybody can get overwhelmed or overworked. So we've got to make sure that we can have the right type of assignment to make sure that we understand the material and that doesn't overload us. So that'll be my job to try to create that, which probably I will fail at. But that is my job.
I have one other question.
You go
I just
ahead.
want to make sure that I'm correct. The finals are due, Shawnee finals are due the week of the 8th through the 12th or something like, or that's when they're giving them?
That is correct. So
Okay.
if you take it
I'm just trying to think ahead of in terms of my teaching as well, what I need to get done. I'm just making sure that I get my finals and everything.
I believe that is correct. So if we said, well, if you take it the 6th, that's too early. If you take it the 8th, that's too, I mean, the 13th, that's too late, according to the Shawnee. I think that is accurate about what we're doing. So, but, I mean, I don't think it's advisable for us to have the exam during that week. I don't think we can have it during that week. Is that right? Is that right? I mean, are we available the 6th through the 13th?
I'm fine with taking it. I just wanted to make sure of getting my papers graded too. That's just what I'm thinking.
I understand.
trying to come up with an idea when I want to take the 6th or the 13th.
I want to do some stuff for the homework, but I also want to open forward any questions that you have. Have you had a chance to look at a lot of videos? Where we at? What's anything bothering you? Anything you'd like to hear about more? Yes, sir.
This is off that topic a little, and I know you're not the one to ask necessarily, but they either haven't received a response or missed it. Do you know why Darborough wasn't here for midterms?
I'm not positive. I think that he had, I think, an ailment, and so yes, sir. I think that is correct, but I'm not positive of that. So I can't give a definitive answer.
Okay.
But yeah, that's one. But we had made arrangements. He and I had made arrangements beforehand. I knew I was covered. Anybody else with anything structurally of the program? I really didn't give a good answer for Richard's question. I don't know. How about for the material? Is it something, do you want me to guide us?
I have that question.
All right.
It seems like in the videos, you just know exactly what test to run, the ratio test or the opening series. How do you know which one?
I don't. I've done the problem ahead of time, so I know it works.
So how would, like, I know that you're asking us, like, in number 2,
Yes.
determine the following series converge or diverge, and I can kind of look at it, and to me, if I look at, like, let's say B,
Yes.
would that be like a root test because it's got an N?
That's a good guess, and I think that could be used.
Okay.
But that's not what I have in mind.
Can you guide us on how to know which, like, you gave us a little summary of,
Yes, and I gave a summary. So this is about homework. Now we're getting to what I was going to go into now.
But I'm struggling with the series and sequences. I'm lucky that when you put it up, I know whether it's a series or a sequence. And I don't know what test to run when. You just, because you've done the problems ahead, you know, I'm looking at this going, I'm not even sure where to start.
Well, one of the things that, okay, so I think that's beautiful.
Is that a does anybody understand my question?
I think that plays into what I want to do.
Okay, good.
Total fog.
So here's, in terms of those problems on your homework. So Christy's mentioning problem 2, okay? All right, look, I want to be very straightforward, and I don't mean to say anything good or bad or, anything that makes people feel bad. These problems, I'm going to say this, are Cal 2 problems, okay? So I know we're in a graduate level class, but we want to make sure that we can not only know the theory, but also be able to apply it, and this is a Cal 2 problem. And the thing that I want to say about it, it might have been a little while since you've seen Cal 2. So if somebody can say, oh, that's nothing more than the law of signs. That's a trig class. That ambiguous case, I hadn't looked at in years for law of signs. So if somebody wants me to do something about it, I'm going to mess up. Does that make sense what I said? So even if I say it's the same level that we're at, you still have to kind of review that. Okay, so Christy's asked a question. What I want to do is, and I did do some problems that were similar, but I want to back up even further than that. So I want to start in this way. Thanks. We're not going to do much now. First thing I want to talk about is this. So let's recall a series, so it's a definition, are associated to a series. I'll say it this way. Let me write it down. Yeah, C sub n, and whatever it does, is a sequence of partial sums I'm going to call them this way, S sub n, so it's got brackets, that means sequence. And here n running from 1 to infinity, where the nth term of the partial sum is equal to the sum, maybe I'll switch indices here. K runs from 1 to n of C sub n. Okay, so that's the first thing. Okay, and so the next thing is that we say,
Why we have this is that okay? It's just,
Your last notation.
yes, this should be a K.
Okay.
Yes, it sure should. Thank you very much. That makes the difference. So the sum is going, at the index is K. That's right. Thank you. Okay, and what we say is the series converges to a number, say C, if and only if the limit as n goes to infinity of S of n, the series of partial sums, equals to C. So this, Christy and everybody else in the room, allows me to look at a particular type of problem that I have in the homework. And so the one that I'm thinking about is on the second page, I guess. Yes, it's problem 6. So this is a Kalamazoo type problem. It's called a telescoping series. That's what it's called. And it's one of the few types of series that we can actually use the definition of a sequence to say, here's what it's converging to, the sequence of partial sums, okay? That we don't have a test for. We don't have to use a test for. I can look at the sequence of partial sums and see what's going on. So I'm going to look at a simple example. It's like this. So I want to do something that's similar to what we've got written there. Consider the series, the sum as maybe k runs from 1 to infinity, of 1 over k minus 1 over k minus 1. And so we look at that. And someone asks us, list the sequence of partial sums for this series. Does this series converge? Or not? And if it does converge, what does it converge to? That's the problem we can answer. Okay, so the way that I would recommend, the way we teach this in Kalamazoo, and that emphasizes the theory, okay? We're talking about the theory, but we need to be applied, is that I'm looking for S of 1. I'm going to write down the first term of the partial sums. Okay, Rich? And so what is that? That's the sum, maybe as k runs from 1 to 1. So this is, remember we had S of n match the n here. Okay? So I'm writing 1 here. Of those terms. So it's 1 over k minus 1 over k plus 1. Well, look, when the series runs from 1 to 1, all we're doing is we're just adding one term.
Why is it plus
It's
one?
minus.
I'd like to make it plus. Yeah, make it plus. I made a mistake. Thank you very much. Make that change. That's what Michael Jackson would tell us. Thank you. So here, what is this? This is going to be 1 minus 1/2. That's what I got. No worries. That's what I got. What's S of 2? That's the sum as k runs from 1 to 2 of 1 over k minus 1 over k plus 1. That's what I mean. Okay, so here, you're adding. Sum means you're adding. So you first add when k is equal to 1, and then to that, you add when k is equal to 2. So I get when k is equal to 1. The first expression is 1 over 1 minus 1/2, and then plus, now when k is equal to 2, I get 1/2 minus 1/3. Well, the 1 lives, is here, but the minus 1/2 and the plus 1/2 would cancel, and you're just left with minus 1/3. Well, what's S sub 3? S sub 3 is the sum as k runs from 1 to 3 of 1 over k minus 1 over k plus 1. That again is these terms, so 1 over 1 minus 1/2, first when k is equal to 1, plus 1/2 minus 1/3, that's when k is equal to 2, plus when k is equal to 3, what do we get? That's right. And the middle terms here cancel, we're just left with 1 minus 1/4. In general, S of n, the nth term of the sequence of partial sums, is going to be 1 minus 1 over, so there's a pattern here, I know the camera didn't see this. When n was 1, we got 1 over 2 here, was the last thing. When n was 2, we got a 3 in the bottom. When n was 3, we got 4. When I just have n in general, what's it going to be? In the bottom. We're okay with that? That's what we're looking at. So, S of n is a sequence. It equals to this. Okay. Why do we look at the sequence of partial sums? Because if that limit, the limit of the sequence of partial sums exists, that's what the sequence that's what the series converges to. So what about this?
Say that again.
So if the limit of this sequence exists, then the series converges to that limit. If the limit of this sequence does not exist, then the series diverges. Okay, Kristen?
Yep. Thank you.
Note, the limit as n goes to infinity of S of n equals to the limit as n goes to infinity of 1 minus 1 over n plus 1. What does this do? So as n goes to infinity, this is 1. What does this part go to? 0. So what's my answer? 1. It converges to 1. That's what it does. That means the sum as k runs from 1 to infinity of 1 over k minus 1 over k plus 1 equals to 1. It's going towards 1. You keep something, you get 1. You know, a lot of things in this course has to do with doing things forever. Infinitely many times. Going towards infinity. That's what a lot of these things, infinite processes, are involved in this course. Okay? Infinitely closed, things of that nature. And here, we can add things if you take a finite number of things. You can add them. We got our normal rules. But when you do things infinitely, some of those rules don't apply. I mean, if you take 3 plus 2, that's 2 plus 3. But you're going to find in the last video lecture of this chapter that the order in which you add infinitely many items can make a difference in terms of what it adds up to. So the order, changing the order, makes a difference. I'll show an example. It's weird. Okay? And I'll show you a criterion that says, hey, it doesn't matter. I'm talking about if you do infinitely many additions, not finite. Finite, we got the rule. I mean, it doesn't matter how you add them. Okay? So that's kind of strange. But anyway, this is our definition way of getting a hold of a series, an infinite series. Okay? That's what we're talking about. working with that definition is tough, and there's only certain types of series that the definition is really profitable to use. One's the type that I just did, and that I asked you about in homework problem number 6. They're called telescoping series. So that just gives you some experience of using the definition of what it means for the series to converge. That's why that problem's on there. Is that okay with everybody? But then Christy asked a very normal question, and that is, that isn't what we're concentrating on. I don't see you use that series, that sequence of partial sums very often. You're normally using tests, which this course has to do with developing those tests in terms of proving them, but also we want to be able to use them. And so problem number 2, she said, well, how do you know what tests to use? Well, first of all, we've got to know the tests. We've got to be able to write them, look at them, find them. So learning them is one thing. And then there are some kind of indicators that would at least to try to help. And one of them, you said the root test. Now, you might try the root test there on that one that you mentioned. But I want to try some, and I did some examples previously, but I want to do some examples that I just happen to have in my hand. Okay, so we have various tests to determine if a series converges or not. Okay. The question is how do you know which one to use? We don't necessarily. We get through experience, maybe a little bit more better feel for what to use. But I'd like to give us a little bit more experience. So I'm going to do some problems. And I had done a few in the lecture. Just some examples. I won't do them now. Let's say I ask this problem. The sum is n runs from 1 to infinity of 1 over n to the 2.8 power. The question is, does this converge or diverge? And the answer is yes. Well, great, John. Tell them yes. We got 50-50 chance. We could guess that too. Answer is yes. Why is the answer yes? So the reason that the answer is yes here, Angie, is that we can recognize this as a certain type of series. It's something called a p-series. Okay? This is a p-series.
When you say yes, you mean converges.
Correct. Thank you. It does one of those, that's right. Okay, so here's what I say. This n equal 1 to infinity of 1 over n to the 2.8 is a p-series. And what do I mean by p-series? It looks like this. The sum is n runs from 1 to infinity of 1 over n to the p. Okay, so if it has that form, it's called a p-series. So the question is, when does a p-series converge? So 1 over n raised to the p power.
Be greater than 1.
For it to converge, yes, ma'am.
No, the p-series test says, and that's what I'm going to write next. Converges if p is greater than 1 and diverges if p is less than 1. Less than or equal to.
1, 0.
Thank you. And so that's what I'm applying. So I can recognize that particular series as a P series and get the answer. So that's what we're looking for. Let me look at another one. So here's an example. Is it okay that I'm doing examples? Is it bother anybody? I don't. So here, so these are examples, but before I move on, this isn't the main part of the course. It's just application of the theorems, the statements. The main part of the course is, do we understand why those statements are true? It takes a lot of effort to learn those proofs. So anyway, here's another example. N runs from 1 to infinity of 4n minus 1 over 3n plus 2. Does it converge or diverge?
Yes.
Yes, it does one of the two. Which one does it do? Anybody want to take a guess?
The diagram.
It diverges. That's right, Evan. Do you know why? Or can you give a reason why?
Well, I remember the example that you did on the videos, and that one is very similar.
Okay. So here, this is diversion. That's right. And I'm glad. That's why we do examples, to remind us.
The L'Hopital's rule and
It's involved. When do we use L'Hopital's rule? When we're doing what type of process? That's right. So what the theorem has to do with the limit? Well, we had the definition, limit of the partial sums, but that isn't what this is. There's something called I'm glad we're here today. You see, I want to tell everybody this. You drive a long way. We better get something out of it. Does that make sense? That's what I think. Okay, so if I can help in some way, I'm grateful. So here, it seems like to me, being able to state the theorems are something that's good. It's the divergence test. Okay? What's the divergence test? So by the divergence test. And maybe you could do, I know you can do something wrong too, but I can help. Okay, so the divergence test, what does it say? It says the following. So this is the way it's written. It says, if this series of A sub n converges, yeah, that's what I said, then the limit is n goes to infinity of A sub n equals to 0. Very funny statement. Okay? Especially with the name I'm giving it. Divergence test. Because it's talking about a series converges. Yeah, so dang. What's the idea here? So, look, if it converges, then this had to happen. Okay? If it's raining, John Whitaker's got an Alabama umbrella. So here's the way that you interpret it. If you don't see me with the Alabama umbrella, it's not raining. And that's the divergence test. So if the limit of n goes to infinity of A sub n is different from 0, then this series diverges. And that's what we use. In our example, sum as n runs from 1 to infinity of 4 to the n minus 1 over 3n plus 2. The A sub n, if you will, is this fraction. We note the limit as n goes to infinity of 4n minus 1 over 3n plus 2 equals to. Well, this is infinity, this part's a line, the top's a line. I'm not saying anything so fantastic. It's 4n minus 1. Slope intercept on the line. It's got a positive slope, it goes off to infinity, go to the far right. So does this guy, 3n plus 2. It's a line. So it goes to infinity over infinity. Well, that from chapter 5, using L'Hopital's rule, because the bottom goes to infinity. And we can say this is equal to the limit as n goes to infinity of the derivative, which is 4 over 3, and that's 4/3. And I'll tell you one thing about 4/3, it's not 0. Is that okay? So that means this series diverges. Diverges by the divergence test. So that's a problem. Here, I want to look at another example next, if it's okay. Somebody's got a question, that's what I mean. All right, let's look at this one. Sum is n runs from 1 to infinity of 3/2 raised to the n.
I do have a question.
I'm ready.
Why is sometimes n is 1 and sometimes it starts at n equals 0?
It can vary just depending on what we're looking at. So it's just, there's no definitive reason, just what you're adding. That's all. But it changes what you're adding, okay? So it's just a matter of a certain term is in there or not. That's all. That's not a bad question. It's just that's what you can add. You could start at n equals to 17 too. You don't have to start at 1 or what we start with. The lowest we'll start with is C. But that's a fine thing to ask. Okay. So here for this guy, we want to know, does it converge or diverge? And so here I want to use with the, first of all, I want to give everybody a chance. Does anybody have an idea?
Diverge.
It diverges. Why does it diverge?
It's a divergent geometric series.
That's right. That's what the answer is.
It's the example of the picture. That's what I did.
Did I do this exact problem?
Yeah.
Is that the homework problem?
No, it's in the notes.
No, it's in the notes right
But that
there.
isn't the homework problem, is it?
No.
You do 7
Oh,
over
that's
5.
okay if it was.
It diverges by the geometric series test.
Because that guy is 3 over 2 is greater than 1.
That's right.
So if it was less than 1, he would converge.
That's right. So here, this is, from the notes, I want to write down, everything precisely. I don't want to make mistakes. So I'm going to look, make sure that I don't miss it. This, what's listed in our book is different than what we present, most of us present in the calculus class, in that we talk about the absolute value for a series with real terms in it. We talk about the absolute values of those terms being less than 1. Okay? But this guy, the way we present it, is the following. It says the following. It says the geometric series test states that if 0 is less than or equal to x is less than or equal to 1, less than, I should say, then the series of x to the n running from 0 to infinity, equal. So not only does it converge, here's something we can say what it converges to. It's 1 over 1 minus x. The way that we normally write that, that's an infinity. Normally we say it's the first term over 1 minus the x. And we think of this as the ratio. And it says if x is greater than 0, it's greater than 1, greater than or equal to 1, then this series diverges. than the series divergence. I know my handwriting's very small back there, but it diverges if the x is bigger than or equal to 1, okay? That's what it says. Is that okay with everybody?
What do you write up there after the 1 over?
It's first term and ratio.
Yeah, so the ratio. First term over 1 minus the ratio. Okay, so I want to explain that to you. Okay, that's what it is every time. So, as another example, let me do this one here. Let's say we start off with n running from 0 to infinity of 1/2 raised to n. So this is a little bit different problem. When I was in college, I had an art professor. I never took him. There was an art professor. Never took him. There was an art professor that when he walked into the room, he walked into a room every time. A certain room he taught in was the exact same room. He didn't go around places. Same room, and the room that he always taught in had a lock on the door. And so I never took this person. But when he walked in, he locked the door. That's what happened. And so if you weren't in the room by the time he came in, it was over for you getting in. And that's what he did. And I never took this person, but it just, the door is locked. That's why I'm telling you this story, okay? But that's why I prompted the story. If I had been a student, I would have knocked on the door the whole hour. I would. I paid to get in that room. And I got up early enough to get here. I don't care if I'm a little late and disturb your play. That's what I would have been. So anyway, I just was reminded. Here, this problem. This is a wonderful problem, in my opinion. The one I'm looking at right now, the sum of 1/2 raised to the n, as n goes from 0 to infinity. And it says something, at least in terms of real numbered series, something that I understood, made a lot of sense to me. Look, it's funny. We're adding up. Did you guys hear me? We're adding up positive numbers. And we're saying it's converging to something. You may already know what I'm going to go with, but I just want to tell everybody. The first number you add up is 1. Then you add up 1/2 when n is 1. So it's 1 plus 1/2 plus 1/4 plus 1/8, and it keeps on going. Well, how can it be that if you keep adding, you converge to a number? It seems like you go beyond any number. But the way that you can think of it, maybe other people already know this problem can be thought of, I am 1 foot from the desk, and at every instant, I go half the distance. So, I start off, maybe I'm 2 feet from the desk. That's where I should start. 2 feet. So the first distance, I go 1 foot. That's the first thing I'm adding. The next, I go half. And you keep going forward. Every instant, you're moving forward. And you can say, well, how can it not add up to something infinite? Well, here's what's very clear. I never get past that desk. So the answer's got to be less than or equal to 2. Well, the distance that I was from the desk. Is that okay? Is that all right with everybody? So that's kind of a nice example. And it turns out this is a convergent geometric series. And what it converges to it's the first term. That's what I said. So the first term, in this case, is when n is 0. What do we get? 1 over 1 minus the ratio. The ratio is the guy that's being raised to the power. So here it would be 1 minus 1/2. That ends up being 1 over 1/2. That is 2. And that is what we thought in this problem. We would cover 2 units, essentially. That's how far you really travel. So right up to it. That's what it's converging to. You keep going forever. 2 feet. Is another very quick example, just to change it up. If I said n runs from 1 to infinity of 3 times 4/5 raised to the n, this is a convergent geometric series. And when it converges to, it's the first term. What's the first term in this series? Over 1 minus, the ratio is 4/5. Is that okay with everybody? I mean, this is arithmetic. I'm not going any further than that. That's what it is. Is that okay?
It's 12.
Yes, that's right. It's 12. Let us do another problem. So, here, as another example, let me look at the sum as n runs from 1 to infinity of 1 over n cubed plus 2. Question is, does it converge or diverge? It looks like a series that we've talked about today. What's it look like, Angie? It sure does. That's what it looks like. It looks like a P series. Okay. This resembles the P series. The sum as n runs from 1 to infinity of 1 over n to the third, which does what, Richard? Does it converge or diverge? It's okay.
Well, that would,
This one, yeah.
that will convert.
That's right. It converges if p is greater than 1 there, the p being 3 in this case. What I remember, you you think of 1 over numbers, that really, as the numbers get big in the bottom, that gets to be adding really small numbers. But 1 over n itself diverges. It's a divergent P series. It's unbounded when you keep adding, okay? But when P is bigger than 1, those things that you're adding are so small, they're negligible. And that's what's happening. So that's what they converge. Okay, resembles a P series. But it's not exactly a P series. So here's what I want you to know. Note that 1 over n to the third plus 2, how does it compare to 1 over n to the third? Just in terms of term by term. Which one's bigger, the right or the left? The right's bigger. The reason that you can see this pretty clearly is that you're dividing by something bigger over here. You're dividing 1 by something bigger, so it got smaller. Is that okay? Is that all right? Then since the sum of 1 over n cubed converges, okay, and these terms, I'll write it this way, these terms are positive. Then this series, it converges by the comparison test. So I want to write up the comparison test just a second. Here's what it says. The part of it that I'm using is this. In particular, it says this. It says if the absolute value of AN, now that can be a complex number, okay? The AN could be, is less than or equal to CN. The CNs can't be complex, okay? Because when I take the absolute value of a complex number, what I get is a real number. And because we're comparing it to something, what we better be comparing it to is a real number. So the A sub n's could be complex, okay? Complex numbers. But the C sub n's here, they definitely are real. And I'm thinking these are terms of series that I'm adding. That's what I'm thinking, okay? So I'm thinking this. If this is true for some n bigger than or equal to n naught. So after some point, n naught, big N naught, after some point in the sequences of A sub n's and C sub n's, the absolute value of the A sub n's are always less than the C sub n's, then, or and, if the sums of the C sub n converge, then the sum of the A sub n's converge. That's what it says. And that's what we're using here. You say, wait a minute. What in the absolute value? What's the absolute value? What's the absolute value of this guy? What is the absolute value of this guy? That guy is himself, because he was positive. Is that okay with everybody? And so that's how I'm applying it, even though I'm not showing all the details, but that's what's being applied. So it's like a p-series. Is that okay? And so we compare it to a p-series. And it makes a lot of sense to me. So to get some kind of idea, without the details of the proof, here's what's happening. We're saying, at least in a real sense, let's put it this way, at least in a real sense, we're saying, hey, if we got positive terms, and we're wondering, does it not add up forever to infinity? Okay? Not go off to infinity with positive term series. Okay? Then what it needs to do is it needs to be bounded by something. Does that make sense? And what's bounding it is the other series. Is that okay? So the one that's bigger than it goes to something. So the one that's smaller, if it's all positive terms, has to not go beyond that. Means it can't run off to infinity. And that's the only way that it can diverge in this situation when you talk about real numbers. Is that all right with us there? Okay, so that's something risky. Okay, type of problem. Let me take another look here, see if there's something else I wanted to do. Well, yes. So here's a final example that I had in mind. It was determined if the sum as n runs from 1 to infinity of minus 1 to the n plus 1 over 2 times n plus 3 converges or diverges. Now, this follows something called the alternating series test. And the reason it's called the alternating series test is because the terms alternate between being positive and negative. So, we're going to use the alternating series test. Let me find it. Sometimes that's what it says. The alternating series test. This uses the alternating series test.
Would you like me to read it too?
Sure, just a second, wait just a second. So give me one more second to see if I can find it, so I don't make a mistake. No, but I might need the help. Urgent location. Yeah, I could use the help. Rearrange it so it's after. I missed it somewhere, of course it's here. But you have it, is that right? So what it has to do with, it says if, go ahead, what does it say?
Okay. It's an A, that's what I had. How many ifs?
Okay.
The absolute value is C1. It's greater than or equal to the absolute value of C2. Nope, other way.
Yeah, that's right, because it's got to be small. Right,
Absolutely. Keep going.
right,
B,
right. And then you have the C sub m, 2m plus 1,
correct. Minus 1.
2m minus 1. The odd ones have to be, really it doesn't matter if it's odd. Has to be greater than or equal to, I'm sure it says,
Yes.
0. And that the C, the 2m, the even ones are less than or equal to 0. It's just that they alternate, okay? It doesn't have to be exactly this form, okay? And then there was something about the C sub n's going to 0, is that right?
The limit.
Yep. As n goes to infinity of C sub n equals to 0, then the sum of the C sub n's convert. That's right.
Under B, does that say 2m minus 1?
Yes, it could say 2m plus 1. Either way is okay.
Okay.
2m plus 1. It's just that the odd number terms we're saying are even, the odd number terms are positive, and the even number terms are negative, or vice versa. Okay? Or vice versa. Is that okay with everybody? It's legible, and we read it. If you need me to say something, I'll say something. Okay, so note, if I look at C's minus 1, if I just compare the n plus 1 over 2 to the n plus 3, if I compare it to minus 1 to the n plus 1 plus 1, so the n plus 1 term. If I just compare these two. So if I compare these two, what you'll find is this one is bigger. Why? As 1 over 2n plus 3 is going to be bigger than or equal to 1 over 2n plus 5. Because that's what those things are. Okay? So that's showing C1 is going to be less, the absolute value of C1 is going to be less than the absolute value of C2 less than or equal to. That's what's going to happen every time. Okay? So it's a decreasing sequence for their absolute values. Then, also, what is C? I'm going to write 2n plus 1. What is that in this problem? Well, that's going to be minus 1 to the 2m plus 1 over 2 to the m plus 1 plus 3. And so this is an even power. Okay? Why? 1 plus 1 is 2. 2 to the m. 2 to the m is even. Plus 2, that's even. Minus 1 to an even power is even, positive, I should say. So this is going to be greater than or equal to 0 because the bottom is positive.
Dr. Whitaker, in the top, the 2m plus 1, is that all exponents?
Yes, it is.
And then down below, those are not exponents?
That's correct.
Okay.
The C sub 2m is minus 1 to the 2m over, and I made a mistake right here. It's not that I put m plus 1 here. What should I put? 2n plus 1. 2n plus 1 is what it should say. It's still positive in the bottom and the top is positive, so that's why we grade that. Here, this would be 2 times 2m plus 3. So here's 2m plus 1. I made a mistake. 2m plus 1. I made a mistake. So here, this is going to be minus 1 over 4m plus 3. Of course, with m being a positive number, this will be less than or equal to 0. And then the last thing we've got to check. Last thing we got to check for the geometric series, not geometric series, but the alternating series test, is about the limit as n goes to infinity of the c sub n, which in this problem was, what is it, minus 1 to the n plus 1 over, what was it, 2n plus 3? It's the limit of that. And so minus 1 to different powers just bounces between minus 1 and positive 1. But this guy, we're taking minus 1 and positive 1 and dividing it by bigger and bigger and bigger numbers, and that goes to, well, the bottom goes to infinity. So what's minus 1 or 1 divided by those types of numbers? 0. It goes to 0. And so that fits the alternating series test. This sum converges. That's what I had in mind, Christy, in terms of showing some more examples.
That helped a lot.
I'm glad. Anyway, it gives us a chance to do the homework a little easier. I'm glad it helped. It turns out, Tiffany, that this problem, last problem, it's kind of nice to emphasize something else. So, Ashley, we also talked about absolute, converging absolutely. Okay, that's towards the end of the number of videos that I've made. Right now, we've got 24 videos up. Okay, and one of the last topics that we've just been talking about is about absolute converging absolute. So here is a definition, and so this, everybody else in the room, has to do with a problem that's on the homework too, that I'm about to cover. In particular, it has to do with problem 5, converging absolutely or not. Okay? So here's the definition. A series, sum, c sub n, converges absolutely. It's absolutely convergent. If the sum of the c sub n, of the absolute value of c sub n, converges. To say a little bit more, I'm going to look at this example here. Say a little bit more. So as a definition, if, let me make sure I say the right thing. If this series of c sub n converges, but this series, the absolute value of the CCN, diverges, then the series, overall series, converges non-absolutely. Does anybody remember from Cal 2? Usually Cal 2 calculus books, they don't call it non-absolute conversion. You know what it's called? That's right. It's called conditionally convergent. I think I wrote that in the notes. But I'm very curious. Does anybody remember this? I'm glad. And I'm glad this way. I'm glad if no one remembers it, because it means what I'm doing here is not something that's repetitive for you, or at least it's something to jog your memory. I'm just checking this. Okay? So this is called conditionally convergent force. And we had that example today, right? We had that example. Now note, in our previous example, this minus 1 to the n plus 1, it was 2 to the n plus 3, is conditionally convergent, or is convergent non-absolutely. I think I started from n running from 1 to 10. I don't remember, okay? It might have been 0. I don't remember. What was the problem? Did I even say?
One bit.
Okay. So I made this claim here. Let's make sure everything's correct with this. So we know that that series converges, right? We did it by the alternating series. The original series I got on the board. What does it take for that series to be convergent non-absolute? It means its absolute value, the sum of the absolute value, does what? Diverges. That's what it means. Is that okay with everybody? So we are going to show the sum of minus 1 to the n plus 1, or the absolute value of it, over 2n plus 3, diverges. First of all, and we say n not being 1. And the sum is n runs from 1 to infinity. Of this absolute value. So let me write down the problem. What is that the sum of without absolute value? What would I write?
Negative 1 squared.
1 over 2 plus 3.
That's what I want. And maybe somebody else heard that. I said it, I heard it. That's what it is. Because that absolute value, what you're taking the absolute value of is either minus 1 over 2n plus 3 or 1 over 2n plus 3. Is that okay? Those types of terms. And the absolute value of that is just the positive version of it, which is what I've written. It's okay? Okay. Now, Allie, that thing diverges. Can you give some kind of clue, Julie, Allie? Some kind of reason. Why, Dennis? Why, Matt? Why we think it converges? Why, Christy? Why? Why, Julie?
Is it some kind of P series, a form of a P series?
It is, but it's not a P series, but it's darn close.
A divergence test?
No, and so stop. That is,
I was gonna say, like, can't you do the comparison?
with a
One,
Oh.
with
P series.
because you got N to first.
Yeah, that's right. That's right. That's what we're going to do. Is that okay with everybody? So, that's why. I'm going to address the other thing first, Angie, what you said. If I try the divergence test on this, the limit is n goes to infinity of this part equals to 0. And the divergence test really doesn't tell us anything in that situation. So if that limit doesn't equal to 0, it diverges. If it equals to 0, we do not know. Okay? That's what happens. So here, I want to say this. This series diverges by the comparison test with a P series 1 over n-ish. So we got to make it match, okay? So I'm going to stop there in terms of this problem. But we got to make it match the comparison test, okay? And so what I can tell you, I'll do it with this. Instead of ish, I'll say 1 over 3n. Okay? That's what I'll do. Let's not leave it. Let's do it all. Okay. Might as well. Let's see what we get. So this is the beautiful thing about mathematics for me. And I don't want to spend too much time, okay, nailing down the details. But if we can do it, let's do it. And the beautiful thing about me is nailing down the details. That is the thing that I like about it. It says this, the theorem. We got to match that. Does that make sense? That's what I enjoy. Don't miss anything. And so what am I comparing it to? What's the comparison? It's the part B of the comparison test, okay? So I want to write it down. So where is it? So it's on this page. It says comparison test part B. Part B, it says, if A sub n is greater than or equal to D sub n is greater than or equal to 0 for n greater than some spot n naught, and if the sum of a dn diverges, then the sum of the an's diverge. It's kind of funny. That way. Of course, we got this from that. the first part was kind of funny to me. The first part of the comparison test has to do with the sequence possibly being complex, the C sub n's. But this part has to do with just reals, because we can compare them. That's how I know it must be reals, because we can't compare complex numbers. Is that okay with everybody? So that's what we have. So these are reals. So how are we using this? I don't want to lose this. I've got this written down. Let's keep that here for this particular problem. Okay. So what am I comparing it to? So I'm saying, note, I'm looking at 1 over 2n plus 3. Okay? And I want to compare it to 1 over 3n.
Now, I know you picked 300. Are we supposed to know how to pick that, or are you going to show us why you picked that?
I'm going to show why I picked it, okay? I think that's a good question, okay? So why did I pick this? Well, here's what I thought. First of all, you know, it's not magic. You try things, and you see if it works. And what you're seeing is a little bit more of a polished, am I in the picture? Is this the right thing?
Yeah.
Okay, thank you very much. I'm sorry. What you're seeing is the polished version. But if I didn't know what to do, you try things. If it works, great, you're done. If it doesn't work, you try something else. But here's kind of what I saw. You know, 2n is 2n. Is the 3 that I got to get. I want to kind of get out of there somehow. Is that okay? And so what I started doing is comparing 3 to n. So the 3n in the bottom is really 2n plus n. Is that okay? So I'm thinking comparing 3 to n. Well, sometimes 3 is bigger. When n is 1, 3 is bigger. Is that okay? When n is 2, 3 is bigger. When n is 3, they're equal. What happens when n is 4? Well, yeah, it's smaller. The n gets bigger. Is that okay? So eventually this guy dominates. Is that all right? Okay. Okay. So eventually, for n being bigger than or equal to 3, okay, which is bigger, the right or the left? So I have to think. I'm going to answer because I need to get my mind on. So here's what I'm thinking. Well, eventually, after n being bigger than, let's say, n is 17, this number in the bottom is bigger than this number. And so when I divide by something bigger, it got... This is like my d sub n. Okay, is that all right? This is like my d sub n. And so what I'm claiming is, if the sum of the d sub n's diverge, then the sum of the d sub n, then the sum of the a sub n's diverge. What do I mean in terms of this particular problem? So if the sum of 1 over 3n diverges, that's my d sub n in my problem. Then the sum of the 1 over 2n plus 3 diverges. Okay, so how do I know whether that sum of 1 over 3 times n diverges? Okay, so here's what I will say. Why does this sum diverge? That's the question. And we kind of hit the main thing, but we haven't hit it perfect. So Ashley, I think you and Dennis kind of combined. I'm not sure. My memory's not good. Maybe somebody else. Combined to say, we're using the comparison test where we're comparing to a p-series. But I'm going to tell everybody, that isn't exactly the perfectly fitting definition for a p-series. Jennifer, the p-series would be 1 over n. Okay? You don't have to write that down. Well, we got this 3 out in front of it. Is that okay?
So here's what I'm thinking. Well, does that 3 matter? And the answer is no. But how would you nail down the detail that doesn't matter?
Pull out the 1/3.
Well, you can, but we have facts about it if you were having a finite series. But here we're not. We're having an infinite. If it's if it's infinite and convergent, you can pull it out. But what about this part? So here's the way I would handle it. We hadn't discussed it. Here's the way I would handle it. So I want to get to this. I know this diverges. Divergent P series. I know that. Since this sum of 1 over n diverges, then its partial sums, its sequence of partial sums, what do you know about them? You know, I'm calling them S of n. It's the sequence of partial sums, this finite thing. Is that okay? What do I know about it? So if the series diverges, what can you tell me about the sequence of partial sums? Say it again. Well, it's definitely something other than 0. What you said is correct. It's not beautiful, okay? Okay, but what you said is correct. I can't say that that's wrong. It doesn't exist. Because if the partial sums, the limit of the partial sums exists, what would that mean? Think back. It means the series, the sequence converges, and if the sequence of partial sums converges, it means the series converges. Is that okay? So this sequence of partial sums must diverge. Is that okay with everybody? This guy must diverge. Okay. But that tells me, so 3 times S of n. I didn't write down the right thing. You guys help me. It's not 3 times. 1/3 times S of n as a sequence must. What it must do? It must diverge. Why must it diverge? Well, what if it converged? Okay? Then if you multiplied it by 3, it would converge. And that means S of n would converge. And we know S of n diverge. Is that okay? That's nailing down the details, not letting anything slide. Is that all right what I just said? And that's what I enjoy about mathematics. And so I hope, Christy, in my explanation here, the 2n were the same. And I got to get bigger than 3. So well, n eventually gets bigger than 3. Is that okay when we're talking about natural numbers? And that's how I decided to choose that. Okay. Well, listen, that's some problems, and that's wonderful that we've done some, hands-on problems, not so much theoretical. But the course is about theory more than anything else. Okay? Is it okay what I've said? I'm going to ask before I move on. You can say, wait a minute, I didn't understand something here. It's okay to ask anything you want. We used to have this physicist when I was in college. He was a fine person, Dr. DeVarty. He's a fine teacher. But we used to make fun of this. We'd say, come by and see me in my office if you have questions. Well, we did. And so afterwards we had this phrase. He always says, come by and see me in my office. I won't help you. That was what we added to it, because we never got anything out of it. Well, I hope that's not what happens with me. But anytime you want to come by or ask questions, please do so. And if I don't get it nailed down the first time, we'll work on it a little later and maybe get something that's more beneficial. So you can ask anything you want. Listen, this is, we're talking more about problems here that are concrete, but we need to do something theoretical. Okay? So I want to ask you this. I had written this geometric series test. It says if, this is the geometric series test. 0 is less than or equal to x is less than 1, then this series converges. Okay, that's what it says. Okay? If x is greater than or equal to 1, then this series diverges. I don't bother anybody. I'm about to ask a question. He keeps asking us stuff and we don't know the answer. We're supposed to know the answer. I don't know if you know the answer or not. I'm just not getting a lot of replies. I don't know. I don't bother with that. That's not generally what we say in Cal 2. Does anybody know what we say in Cal 2? It isn't that x is in between 0 and 1 like that. It isn't x.
R?
Yes, but it isn't just R. R is that ratio. You know when I wrote down here ratio, that's when we use R, Evan. It stands for the ratio. Remember I wrote down first term over 1 minus R? When I'm going to have it isn't that. Does anybody know? Okay, we don't usually say x. We don't have x being positive. What we say is this. So here's the statement I want you to try to prove. Okay, I'm asking right now. See if we can do it. Okay? Don't be bothered. I don't know where to do. I don't know what to do. I'm going to help you. State if the absolute value of x is less than 1, then the sum of the x to the n runs from 0 to infinity, converges. That's what I'd like to see if we can do that. Just that statement. Can you prove that statement? So I'd like to see if we can prove that statement. So I'm going to give people just a minute, okay? I don't bother anybody.
Do the limit.
No, I don't think so.
Breaking cases,
Good.
use the geometric test for the positive and the alternating series test for the negative.
It didn't. Well, I guess it does alternate. Maybe. I think that might work. I think that might.
You get the second, where it's negative.
I think that's worth pursuing. Okay. Man, I think that might work. I haven't thought through it, but I think that's definitely worth pursuing. Okay? And Christy, in that sense, it is going to involve a limit because of the alternating series test involved in the limit. So it's something we're trying. It's not what I got in mind, but I want to tell everybody, and it doesn't matter, you know. It's not. I applaud the thought process. I think it has a good shot for it. It's not what I got in mind. I'm going to say what I have in mind then, so that I can read it. I got in mind the comparison. You know why I got in mind the comparison test? Because it's got absolute value. Then the comparison test have the first part. Isn't that right? So here's what I want. Well, I tell you one thing. So let's talk about this proof, okay? Here's what I'll say. Note whatever x is. Okay, well, we're going to let absolute value of x be less than 1. We want to show that the sum of x and n converges. Well, here's the first thing I would do. So I think we can use the comparison test. That's what I'm thinking. Okay, what is it? It says, hey, if the absolute values of the C sub n are less, was it A sub n? Is less than C sub n, less than or equal to C sub n, and the sum of the C sub n's converge, then the sum of the A sub n's converge. Isn't that what it says? Is that right? I think that's right. Let's make sure. I don't make a mistake. It's easy to make a mistake. Yeah, that's what it is. Okay. Well, it has here for n, for some point, sorry, n not being bigger than, n being bigger than n not. Okay, it is. Okay. Okay, so, here's what I want you to notice. Note the absolute value of x to the n is less than or equal to the absolute value of x to the n. I didn't say anything wrong. Okay. This is the absolute value of a sub n here. This is the absolute value of the, I'm sorry, it's not the absolute value. This is like my C sub s. Is that okay? But what is this equal to? It's also equal to the absolute value of x raised to the n. Is that okay? Is that all right? Those are the same. So the absolute value of x to the n is the absolute value of x raised to the n times. Okay? That's what we have. So this can be thought of as my C sub n as well. This part right here is the C sub n. Well, since the absolute value of x is less than 1, and we know it's bigger than or equal to 0, that's right. And that puts me in a position where the role of x in the geometric series is being played by, over here and where my work is being played by this guy's role in the statement of this theorem is being played by the absolute value of x. Okay, so here, the sum of the C sub n's, what does it do? The sum of the C sub n's converges. So that means that the A sub n's converge. What's playing the role of A sub n? Well, the absolute value of A sub n was x sub n. Yeah. So that says the sum as x raised to n converges by the comparison test. I say comparison. That's the right thing to say. This part wasn't by the comparison test. This was by the geometric series test. Now, I think your suggestion will work. I definitely would pursue it. Okay?
This seems easy.
I thought of it beforehand, okay?
Yeah.
I didn't explore yours, but there's nothing wrong with exploring it. I know the handwriting's real small, but
we got a couple more things to prove on this alternating test.
Yeah, so maybe it's easier this way, I don't know. But there's nothing wrong with trying something. And I want to tell everybody, if it doesn't work, you just say, well, it didn't work. I mean, and it's not, I mean, nobody feels good about it. We'd like to be done so we can watch the ball games tonight, you know. I'm going to watch the ball game tonight. We'd like to be done, but if we're not done, we don't think it's a disaster. You go on. At least that's the attitude I want to stand on. That's the right attitude. You just keep going. Okay, didn't work. I tried again. That's what's beneficial. All right. So that's kind of what I wanted to cover. Are there further questions of me? Things that you'd like to see done? Some other things? Maybe something from homework. Maybe something from, we're not done. We've still got about 20 more minutes. Are there other things? I just want to give a break for you to get a chance to ask. If not, I'm going to talk about other things.
I get an explanation of something that's done in the past, and I think I have an idea about it, but I'd like a little bit, especially with like the, when you're doing an epsilon proof, there are a number of times where you say, given epsilon's greater than 0, and then you go, A minus B is less than epsilon, and so they're equal to each other.
Yeah, you'd like to know why that's true. Okay. Okay, so it's easy to mess this up. So I might mess it up. But if I mess it up, so I'm going to spend some time on this because it's easy for me to mess it up. I think most people know what they're doing to do it very easily. But sometimes I mess this part up. Okay, so it's just a law with me. But if I do, I'll just do a video, part of the video. Okay, but this is what it is. Here's the way I'll say it. I'll say something like this. This is the statement of it. If 0 is less than or equal to t is less than epsilon for every epsilon greater than 0, then t has to be equal. So here's the idea, man. Everybody else knows. What is this statement? What this is saying, hey, you've got this quantity, and it's less than or equal to this other quantity, but this quantity we know is but it's smaller than anything you give me. It has to be zero. That's what it's saying. It's smaller than anything you give me. And that's kind of the basis for what we're talking about. So here's the proof. Suppose not. That's right. Suppose 0 is less than or equal to t is less than epsilon, but t does not equal to 0. And here I should say for any epsilon greater than 0, but t does not equal 0. So this one I can do, okay? So that's what we're looking at. Things, similar statements are similar to it. A little bit careful, more careful than something we add to it. This one I feel comfortable with. So suppose t isn't 0. That means that t, because we're having a stipulation of greater than or equal to 0 now, it means that it's got to be a positive number. So And now you can almost treat it like one of these epsilons. So, if you will, t over 2 has to be greater than 0. And we can think of that as our epsilon. Thus, by hypothesis, by what we're assuming, okay? We're assuming that t is less than any positive number you give me. So it has to be less than this positive number. And that's the contradiction. T can't be less than half. So that's the contradiction. So that when you see this epsilon is greater than 0 is arbitrary, that's the type of argument. The distance between these guys is less than anything. So they better be the same. Is that okay? That's the arguments that are being used when we say epsilon is greater than 0.
So because this thing can be anything, it can shrink, it can be positive and shrink to 0. The only way that thing could happen is if these two are equal. Okay.
That's the type of thing.
Okay.
With this being bigger than 0, okay?
Okay. Where?
Okay, so you gotta have that possible. So a lot of times we have absolute values involved, okay? Or we know that that's bigger than or equal to 0. Yes, sir. That's the idea. Is that okay with everybody? And now we are using that. That is correct. It's coming up. I say every once in a while, hey, since epsilon was arbitrary, these guys had to be the same, or some inequality exists. Sometimes it's for inequality. Okay. Anybody else with anything?
In the homework, you have, number 3 is find the radius of convergence for the following. I'm looking through the notes, I can't find radius. Do you happen to know what it's between or where it is?
Yes, ma'am. I sure can find it. If you give me a second. So, what is it? I'll write it down just a second. The book too.
Just because I was looking so that I could tag it in my notes, then I know where to go back and look, but if somebody else can find it.
Yeah, it's something I'm looking at right now. So it's on page 69. So where it comes after is the power series. So
I'm not even looking in the right spot then, that's why.
I want to make sure. Did I? Yeah, I did.
So right in the 22.
Thank you. Oh, that's it.
And so that's been brought up, talk about the radius of convergence.
I was trying to put it back with curves and stuff, that's why. I was
it's
I
not.
was way in the wrong spot.
So here's what I want to tell you. So let me write up the definition that we gave for it. And
You're right, it is right again.
That's the last thing.
It's the last thing.
And I haven't watched 23 yet, so I don't know what it is.
And you have examples there, so it's fine. I just couldn't find it.
that's a great. Okay, I'll do something. Just a second. Give me 1 second. Okay? So here's our definition. The radius of convergence has to do with the power series. And so we're saying, when does the power series converge? For what values that are in the power series? And the power series can look like something like this. So we have this power series. It looks like some numbers times the variable, which could be a complex number, so we're going to call it Z, to the n. That's a power series. And usually we start from n running from 0 to infinity. That's usually where we run. So as some examples. N running from 1 to infinity. of n cubed z then. That's one example. 2, n run from 1 to infinity of 2 to the n over n squared z to the n. These are power series.
1 or 0.
Yeah, so 1 or 0. It usually we start with 0, but because I've got n here in the bottom, 1. Okay, and I'm going to let this be 1 as well. Usually we start with 0. It affects what function you're writing down, but it's okay to write either 1 based on the expression, okay? Those are examples. And what is it that we're talking about? We're talking about where does it converge? Okay? Or what values of z does it converge? And so here's the definition. So the definition, given a series, it's a power series, sum c to the n z to the n, then the extended real number r big R is called, and when we say extended real number, big R, it could be plus or minus infinity or a real number. Is the number such that if the absolute value, it might be a complex number, is less than R, then this series converges. And if the absolute value of z is bigger than R, then this series diverges. We don't know what happens when the absolute value of z is equal to R. It depends on the problem. And I do some examples where if you look at when the absolute value is equal to R, it converges, and you look at the absolute value is equal to R, it diverges, the power series. Okay? So it changes depending upon what the z depends on. So you can't really say anything. But that's what we're talking about. So everything in the complex plane, x, y axis, this imaginary part, it's the real part. When you talk about the absolute value of z being less than number, you're talking about a circle centered at 0 of a certain radius, or r. So everything that's in there, if you stick it in, any number that's in there, in that circle of radius r, centered at the origin, it forces this series to converge. And if you're outside of it, it diverges. Is that okay? Every once in a while, r could be infinity, meaning it converges for everything. Is that okay? And so I have two examples here. So they're similar to what I was asking about. Okay? And you can use either the root test or the ratio test to help you with these problems, and we did examples of them in the video lectures. Okay? The root or ratio. Oh. But why don't I try to tackle one here real quick, okay? So as an example, I'll do this. Okay? No, you know what? I'm going to do two. I'll do two. So as example, we will show, or we will determine the radius of convergence for sum of n runs from 1 to infinity of 2 to the n over n squared c to the n. Okay. So here's the fact that we're going to be using. It's based on the root test. It says if alpha is equal to the lim sup, n goes to infinity, of the nth root of c to the n, absolute value should say, yep. Then r is equal to 1 over alpha. So I want to determine the radius of conversion. I'm going to use this. This is the absolute value of, it's not C, C sub n. Okay? And what am I talking about? I'm talking about this series, C sub n, C to n. Okay, that's what I'm talking about. So that's the theorem that we did do. Send those videos. Is it? I want to ask this question. Sometimes I say, hey, I just put up these 2 video lectures. Is that beneficial for me to say, or you guys notice?
I like it.
Does it make a difference sometimes?
I like that.
Okay.
Sometimes if you're ahead or behind, it reminds you to come if there's more waiting.
Yeah.
Okay.
You're now officially behind. Because you haven't watched them and I've added more.
I can't tell you how many times officially somebody says I was behind. Hey, behind. I don't know.
I see this all the time. We're officially behind.
Okay, I'm ready to do this problem. I've done this problem, so here. For this problem, here's what I'm going to look at. Note the lim sup, which in this case is going to be the same thing as the limit, okay? It's in infinity, of the nth root of c sub n. This number is 2. The c sub n is the guy that did the z sub n. It's there. So I'm going to take the absolute value of 2 to the n over n squared. That's 2 to the n. Well, that's the lim sup. As n goes to infinity. Let's see. This would be, if you will, the nth root of 2 to the n over n squared. Because the absolute value of that guy is itself, because it's positive. So we'll finish this one up and we'll call it quits. And I'll post this. Okay, so the nth root of 2 to the n is just going to be the top. The nth root of 2 to the n, actually. 2.
Sorry.
You didn't say anything wrong. It's 2, and then this would really be n in the bottom. Isn't it n squared? So isn't it? So I can make it minus 2 over n. Is that okay? And that's what I'll do. Well, the 2 can be taken out. And really, I said the lim sup and the sup and the limit will be the same. Really, provided the limit is this. Okay, so let me see. Let's note. Let's consider this. Let's examine. All right, examine. The limit as n goes to infinity of n to the minus 2 over n. Okay, when I look at this, this is the form. It's a form of infinity. Well, this is the power here. As n gets really huge, minus 2 divided by really huge goes to 0. That is an indeterminate limit form. It's not a L'Hopital's form, but you can put it in that form, or at least look at a problem similar to it to get that type of form. Is that okay with everybody? And we did this in videos. We'll say, well, consider, to get this answer, consider the limit as n goes to infinity of ln of n to the minus 2 over n. And so the reason that we take a look at the limit not of this problem anymore, but ln of this problem, is because of properties of logarithms that allow me to move the power as a factor out front. So I say, hey, it's the limit as n goes to infinity of minus 2 over n times ln of n. And now this goes to 0 times infinity, which is still an indeterminate limit form, and is still not a L'Hopital's rule form. But we can change that one more time. We can say that's equal to the limit as n goes to infinity of minus 2 times ln of n over n. And when I look at that, ln of infinity goes to infinity. It's like minus infinity over infinity. Now we look at rule form. So I use L'Hopital's rule. So what's that equal to? That's equal to, well, take the derivative off. It's minus, oh gosh, it's got a limit. It's minus 2 times 1 over n, all over 1. Well, that's the limit as n goes to infinity of minus 2 over n. Well, I can do that. That's 0. So I've got the limit of the kind of associated problem, but I haven't got the limit of what I wanted. But it's not hard to get that. So, the limit as n goes to infinity of the problem I want here, n minus 2 over n. What's it's equal to? So I might have written this before. It's the limit as n goes to infinity of e to ln of n to the minus 2 over n. Because the e and the ln will cancel out. Okay? And because e is a continuous function, and this is the composition of these functions, when you take the limit of this, you can bring the limit inside the outer function involved and the composition. So it's really e to the limit as n goes to infinity of ln of n to minus 2 over n. But I just found that guy, didn't I? I did all that work over there. I did all that work over there and I got 0. So this is really e to the 0, so I get 1. Is that okay with everybody? That's what I got. I got 1. Is that okay? Okay. What'd you say? All right. So I got 1 for that, but I got to be careful. What did I do? I found this, right? So this says that the lim suit, what I wanted, lim suit of 2 to the n minus 2 over n. Well, this guy was 1. So I get, this guy's 1. So I just get 2. Is that okay with everybody? In my theorem that I started this problem with, that was denoted by alpha, and that's not the radius of convergence. The radius of convergence is 1 over alpha. Look, I don't bother you, but so R is 1 over alpha. This is alpha. We're calling that. That's called alpha. That was terrible. Called alpha. I watched some of this TV. That was a commercial called Alpha. That's the insurance company. I'm going to write down R. It's 1 over alpha, which is 1/2. I said, Christy, you could also use the, because you wrote it down.
Oh, I'm sorry. The ratio test and the root test.
That's right. And so this is kind of the root test version of it. Okay? What if you were to use the ratio test? I mean, that's another test out there. Look, our time's up. You may say, well, I want to get the heck out of here. What's he doing? It's time to go home. Let me do this one more problem, 3 more minutes. Okay, same problem, ratio. And then I'll call it quits if that's okay. One more problem. Same problem. By the ratio test, the ratio test says you look at the limb soup of the next term over the previous term. That's the value. So by the ratio test, what was the problem? It was the sum of, I've forgotten. It was 2 to the n over n squared, c to the n. Ratio. Ratio test says, look at this. It says, look at the limb soup. 2 to the n plus 1 is a to the n plus 1 over a to the n, okay? Which is our problem. I'm replacing n. The top part says a to the n plus 1. It's the top part is I'm replacing all the n's with n plus 1. I'm writing this down just as a notation for us, okay? So it's 2 to the n plus 1 times z to the n plus 1 all over n plus 1 to b.
Squared.
All that over a sub n, which is 2 to the n squared times z to the n. You look at this. All right. Here you flip the bottom and multiply it by the top. We're going to get 2 to the n plus 1, z to the n plus 1. That's a 2. And then this is n plus 1 to b squared times what? Times the bottom now is going to be n squared, isn't it? I'll flip it. So it's n squared at the top, and then the bottom is 2n times z to the n. Okay, that's what it is. Which equals. And then n goes to infinity. That clock's wrong. This is 2. We'll do cancellations. I've got an n squared over n plus 1 to b squared. The z to the n plus 1 over the z to the n leaves the z in the top. Okay. Look, n's what's changing. So the 2 and the z, which I can pull out the absolute value, see, outside of the limit is what I have. And now I've got n squared over n plus 1 to b squared.
You're not on the camera.
I'm not on the camera. Okay. Thank you very much. I'll move the camera.
Is that 2 absolute values Z on the last one?
Yes, ma'am, it is. I'm not on the camera. Why? I wasn't on the camera to start with?
No.
Oh, my goodness. For a half hour.
No, just, we're passing out chalk.
I got chalk. I mean, I got projectiles up here, Julie. Be careful. I mean, no one will know if I throw it at you. I'll deny it. Say it's not on videotape. They can forge anything now. Thank you. Whatever was said during that period of time. The video quality is not beautiful, but it's better than what it used to be. The first time that we taught a graduate class, the students said watching me was like watching a Godzilla movie. Because my mouth was moving, but it didn't coincide with what was being said. I really didn't appreciate that. They said it. I said, well, this group's going to attack Token. This is 2 times absolute value, see? What is this? When you use L'Hopital's rule, you know what you get? The highest power term here is n squared. What's the highest power term here? N squared. Well, you use derivative. What are you going to get? Go ahead, Julie. 1. That's what this is. It's this. The ratio test says, hey, that guy's going to converge if this thing right here is less than 1. So if this guy converges, that means the absolute value of z has to be less than This is easy, okay? Yes, ma'am. And that's the radius of convergence, r equal to 1/2. The absolute value z's got to be less than this to converge. If you're not, otherwise you diverge. That's it. Ladies and gentlemen, I've kept you long enough. I want to thank you very much for your patience. And then we got good time.
I'll get more, but.
Thank you very much for coming.
Thank you.
I didn't do it.